Let's now explore finding the areas of surfaces of revolution. We are going to be able to do this using Cartesian equations and parametric equations, and we're also going to have to be mindful of which axis we are rotating around. Now, hopefully you've watched the theory video before this, and as I've mentioned previously, within each of these equations, if we look at this portion along with the integral and the dt or dx or dy, that was the length of our curve. When we multiply the length of our curve by 2 pi y, what we're effectively doing is finding the surface area of a bunch of cylinders, because you might remember when you've done surface area in the past, for a cylinder it was equal to 2 pi r times h. That 2 pi r was about the circumference of that cylinder, and h was about the height of that cylinder. So what we're effectively doing here is in front of each of these, it's like our 2 pi r. It's going to take our curve, break it up into lots of teeny tiny cylinders, which each have a different radius r. And depending on which axis we're rotating around, it's going to change it. So when we're rotating about the x-axis, y becomes like the radius of our little cylinder. And the height of that cylinder, well, that's going to depend on the length of the curve. So that's why the length of the curve formula appears in there. So please, if you haven't done so, please make sure that you check out the theory videos linked to this so that these formulae make sense. So when we're doing these questions, we previously talked when we were doing volume that we needed to check if we were doing volume or surface area. And that's really key because all of these questions we're going to be dealing with surface area. So it's useful that we've gotten into the habit of checking if we're doing that, because now we're going to need to consider the surface area formula. So we've always got a 2 pi and then either a y or an x. I often like to put the 2 pi out the front in my calculations, but it makes no difference. But what we might need to consider though, is sometimes we're asked to find the total surface area. All of the equations above, they will find this surface area, that curved shape that's sort of like the outside of a glass or a bowl, but we might need to manually add on this circle here. I know it may not look particularly circular because we're looking at it side on, and this circle here. So this is a three-dimensional shape. It's got circles. We're just looking at it from the side. So that's what's being referenced down here. A is found using the equations that we mentioned above, and we might need to do pi r squared if we're looking at this particular circle, so I might do that in green. So this circle here, pi r squared, well, the radius of that is going to be the value of the function being represented by this line segment here. So the value of the function for that particular value of x, so that's f of a, and then this circle is pi r squared, but we're doing pi times the value of the function at x equals b, which is the center of this circle here. So just take note if you need to find the total area of a solid of revolution. They might ask for an enclosed shape. This would be an enclosed shape. So that's a word that they may use. Sometimes they might say that part of it's open and part of it's closed. So perhaps this could be a bucket, and this side that I've erased here, perhaps that is not included and the green part is. So just be mindful of reading the requirements of the question and take note of any particular words they use to describe it. Okay, let's look at some examples. We want to find the area of the surface, aka surface area, generated by revolving part of a curve, that's y equals x cubed, from the point 0, 0 to 2, 8. Now they've given us points here as a little bit of a trick because we need to be aware of whether we're going to have terminals in the x direction or the y direction. Well, when we're finding surface area, you might like to write SA or maybe just area or something like that. I don't mind. Now, if we're rotating about the x-axis, that's the key thing here. We've already, number one, figured out we're looking at a surface area, but number two, we're looking at the x-axis. So when we are rotating something around the x-axis, it's going to be this version of the formula here. We are interested in, because we're looking at the x-axis, we need to know where we're going from and to in the x-axis, and we're going to have dx at the end. So let's note down our formula. So what will our terminals be? Because we're interested in the x-axis, we need to know where we're starting and where we're going to. and that's going to be the x portion of this coordinate. So we're going from 0 to 2. Now, instead of y, we know that y equals x cubed. So we're going to put x cubed in where y was. And that's good because we don't want to have y's in the end inside of this integral because we're integrating with respect to x. So that should also help prompt us. Now dy dx, I might just do that on the side here. Dy dx, that's easy, 3x squared. Take the power down the front, take 1 from the power. So when we do this square root, we're going to have 1 plus, and then in brackets, 3x squared. And we must ensure we square that. And finish off the line with the dx. Okay. Let's see what we can neaten up inside of there. We've got an x cubed out the front. All we can really do at the moment is make that 9x to the power of 4, and then dx. Okay, looking at what we've got here, I think a bit of u substitution is going to be useful. I think because we've got an x to the power of 4 and an x cubed here, that's going to help us out a lot. So let's let u equal not just the 9x squared, but let's let u equal 1 plus 9, not x squared, x to the power of 4, I mean. So du dx would therefore be 36 x to the power of 3. Now we need to also change those terminals because we can't have it in terms of x anymore. So if x equals 2, that was the top terminal, u is going to be 1 plus 9 and then 2 to the power of 4, which is going to be 145. And then x equals 0, that would be u would just equal 1 because we have that 9x to the power of 4 there. Sorry if you can hear birds squawking outside my window. Okay, let's put all that together. Because we only had x to the power of 3 inside of that integral, let's put a 2 pi times 1 over 36. Because we know that du dx is 36x cubed, but we only had an x cubed inside of that integral. So then we put this, and we've got 1 to 145. We've got the square root of u, and now du. So neatening this up, outside we're just going to have pi on 18, and we're going from 1 to 145, square root u, du. Okay, let's actually integrate that. Still got that pi on 18 hanging out at the front. We're going to have u, we could have written that, instead of square root u if we wanted, we could have done a half u. That can help conceptualize it a bit better. So we're going to add 1 to the power. So u will be to the 3 over 2 now, and divide by that new power. We could do 1 over 3 over 2, or we could just write 2 over 3. Terminals of 145 and 1. Now, a good thing to note here, it might be possible that changing the terminals to be in terms of u could cause you a little more work. What you might prefer to do instead is have it as an indefinite integral and then substitute in the x values once you have eliminated u and changed it back to be in terms of x. That's totally up to you. Regardless of what process you use, doing that algebra, you should eventually simplify it down to be pi on 27, and then I think we should have 145 root 145 minus 1. And because we're dealing with an area, that's going to be square units. So check that algebra and see. You might like to try using the terminals that we changed it to, or putting it back in terms of x and using those original terminals. Let's now look at the next question. Okay, here we have a semicircle. We're told its radius, and we're defining it with these parametric equations. X is r cos t, y is r sin t, and we know t is in between 0 and pi. We want to find the area of the surface, aka surface area, generated by revolving this semicircle about the x-axis. So we've done our 2 checks. Number 1, surface area. Number 2, we are rotating about the x-axis. So what formula do we have for this? Let's put in the general version. I'm just going to write area here. You can write SA for surface area if you like, but I think area is preferable. So because we're going around the x-axis and it's a parametric equation, let's have a look at the formula sheet extract to see which equation we need. Okay, so here we go. Surface area, and we've got parametric equations, and we're rotating, or in this case the question says revolving, around that x-axis. So this is the equation we're going to use. So let's put in the general version first. Okay, so we have that in this form. For this, we're going to need to know dx dt and dy dt, so perhaps we do that just up here. So dx dt cos goes to negative sign, so that would be negative r sine t, and dy dt, sine goes to positive cos, so that's going to be r cos t. Great, we're now ready to substitute. Okay, so we were told that t is in between 0 and pi. We've got 2 pi. Y is this. It's r sine t. So where we used to have y, we're going to have r sine t. Now we've got our square root ready. We're going to have dx dt squared, so that's going to be negative r sine t all squared plus, and dy dt all squared, so r cos t all squared and dt. Now 2 pi r here, these are just, it's a semicircle with radius r, so that's just a constant. So I'm going to put that outside of our integral. So we've still got that sine t there, and we're going to neaten up what's inside our square root. So that's going to be r squared sine squared t plus r squared cos squared t. It's always great seeing a sine squared t and a cos squared t. Oops, got so excited I wrote the sine squared there. Reason being, we've got r squared and then sine squared t plus cos squared t. That's just 1. So this nicely just goes to 1. This, I'll just put a note on the side, this all just becomes square root of r squared, which is r, and because we already had an r here, I'm now going to make that r squared because we can just take that outside of the integral. And that really simplifies our lives because now we've got a 2 pi r squared, again that r came from this, and then the integral, maybe I'll move that down. And that integral, again, from 0 to pi, but now all we have inside there is a side t, dt. Really nice. So evaluating that integral, that sine t is going to go to negative cos t with our terminals. Also being careful with signs there. So we have minus minus 1, so that becomes positive 1 plus 1, so that's going to be 2. And that means we're going to have 2 times 2 pi r squared, so 4 pi r squared units squared. Okay, new question. We have another Cartesian version. We know it's Cartesian because it's just in terms of x's and y's. We're told x goes between 0 and 4 inclusive. It's rotated about the x-axis to form a surface of revolution. We've determined we're looking at surface area. We know we're looking at the x-axis. So we're going to need the version that has from x1 to x2, 2 pi y, could of course put that 2 pi out the front, and then 1 plus dy dx squared dx. So we're going to need to know dy dx. So we know we could write that as y equals x to the power of a half, meaning dy dx is going to be bring the power down the front, half, take 1 from the power, negative a half. So you could write that as 1 over 2 and then root x underneath there as well. So let's get to the substitution step. I'm going to take that 2 pi out. x1 was 0, x2 was 4. Y was root x. So that y has just come down and become this. And then we have another square root, 1 plus dy dx, so 1 over 2 root x, square that, dx. Okay, if you continued with the algebra of this and eventually used U substitution, you could solve this by hand, but let's look at this one as if it's on paper 2 and we'd be using a calculator. Any more algebra would not be necessary. I would be going straight to this step here where we actually pop things in. And I did want to have that 2 pi out the front, so let's go back there. So let's have 2 pi, we're going from 0 to 4, and then we're going to type this in as it appears. Oh, take care, I nearly missed that square. Okay, so we get something that looks like this. Let's perhaps factor that out. Okay, rather than factoring it, I did mean combine. Okay, so we have 17 root 17 minus 1 times pi over 6. So let's put that pi over 6 at the front. And you could, of course, confirm this with your calculations by hand. And that's the surface area, so it's units squared. Now, continuing on this question, it says if the shaped form is closed. Now, if we do a quick little sketch on the side here, if we're looking at the graph of y equals x squared, it's going to look something like this. So when we rotate that around the x-axis, we're going to get this sort of, I don't know how to describe that, this curved kind of shape here, where we've got an open circle on the end. So that would be from rotating this around. There we go. So this kind of shape. So what that means is we don't have any circle going on here because it just reaches a point. So we need to add on the area of this circle. So therefore, total area, that's just going to be the original area plus the circle. So that's going to be pi on 6, 17 root 17 minus 1, plus we're going to have pi times. Now, what will the radius be here? It's going to be the value of the function. We'll say y equals f of x for a moment, at this particular value of x. And we said we're going from 0 to 4. So the center of this circle is going to be 4 units in that x direction. So all that means is we need to find the value of y when x equals 4. And that's going to be like our r. So I'm going to put the value of f of 4 squared. And when we said x equals 4, y was just equal to 2. And we're squaring that. Because don't forget we had this external square. So we have pi over 6, 17 root 17 minus 1 plus 4 pi. And if you were so inclined, you could write it like this. And then that would be plus 24. Because we've taken pi out as a common factor. It's like we multiplied by 6 over 6. And we took that pi out as a common factor here. Okay, rather interesting curve we have here. It's defined as x equals a half, and then in brackets e to the power of y plus e to the power of negative y. And in this case, we're told that y is in between 0 and log base e of 2, and we're rotating around that y-axis here to form a surface of revolution. So we're looking at, again, surface area, and we're rotating around the y-axis now. So to be able to do information with this, first off, let's look at the formula that we need. Okay, here we are. We need the surface area. We're looking at Cartesian form and about that y-axis. So let's transcribe this as our first step. So there we go. We have an expression for x. We need to note down what dx dy is. And isn't it nice when we've just got e to the power of y's there? That's going to give us a half. And we're going to have e to the y, and because we have e to the negative y here, that's going to be minus e to the negative y. Okay, so we've got dx dy. Let's pop that into our integral. So y was going in between 0 and log based e of 2. I'm going to write that 2 pi. I'll take it out later. And we've got x is going to be times 1 over 2 e to the plus e to the negative y. We're going to have to be really careful with our signs here. So that was just the substitution of x. Now we've got square root of 1 plus dx dy squared. My apologies, I meant to put in the actual value of dx dy. Make sure you square it and make sure you pop that dy at the end. Let's now go ahead and put this into our calculator. So this one was so long to put into the calculator, I had to turn it on the side to be able to show you the answer. You'll see, even though it was in standard mode, the CAS was not able to show this in exact form. If you go ahead and do the algebra, and with this in here, my big hint to you algebraically is to rearrange and reorganize this into a single bracket with stuff inside it squared so that you can eliminate that square root. If you go ahead, you should actually get this as the exact answer. So it would be pi on 2 and then in brackets 15 over 8 plus 2 natural log of 2. So that's what it would be in standard form. So I do encourage you to go ahead and do the algebra to see that you get that. But yeah, this was a very involved question, but on the CAS, quite straightforward. So yeah, I encourage you to try this one by hand, confirm that you do get that answer that I had on the CAS as your final answer if you rearrange it there. But yeah, really fun question. So remember, with questions like this, are you doing the volume or the surface area? Which axis are you rotating around? I guess another consideration is, do I have it in parametric form or do I have it in Cartesian form? And when you're doing surface areas, do you need to consider another shape added on at the end? With the question that we did here, it's just finding this surface area that we had. It's this interesting kind of shape here. But if it asks for the enclosed areas, we would need to consider the circles on either end in this particular shape's case. So take care with the algebra, make sure you're considering all of those things that we mentioned before, and good luck with your practice.